Good afternoon. We are going to work with some theorems that deal with three parallel lines or three-line comparisons. And then we're also going to go through what a flow proof is. And we're going to take a chance to practice writing a two-column proof as a flow proof. Flow proofs are one of the ones you need to know how to read at a minimum. All right, so here we go. First one, comparing three lines, Theorem 2-8. In a plane, if two lines, and there's a word missing there, so put the word are, if two lines are perpendicular to the transversal, in a plane, if two lines are perpendicular to the transversal, then they are parallel. All right, so this one we're going to show this a little different today. We're going to show this as an if-then. Most of your proofs have an if, what comes first, and then they have a then, what is the result. So in this one, what comes first is you have a transversal, and then you have two parallel lines. Or actually, sorry, not parallel, perpendicular lines. So you start with the first line being perpendicular, and the second line being perpendicular. That's what you start with. By the way, an equal sign followed by an arrow means if then in logic notation, so feel free to use that. So we know that two lines are perpendicular to the transversal. What do we get out of it? Well, if they are both perpendicular to the transversal, then we know that they have to be parallel to each other. This actually makes a lot of sense because if line 1 is perpendicular to a transversal and line 2 is perpendicular to a transversal, then we can use the theorem if corresponding angles are congruent, then the lines are parallel. So because these two are both 90, they are congruent to each other, and the result is you know that line 1 and line 2 are parallel. So this theorem just cuts through that in specifically a perpendicular measurement. But actually, if either one of the measures are, as long as they're the same, they can be anything. If corresponding angles are congruent, the lines are parallel. This is just an easier one because it deals with perpendicular. Okay, 2-9. Two lines parallel to a third line are parallel to each other. Okay, so here we have line 1 and we have line 2. What this does is it compares line 1 to line 2, and then it compares line 3 to line 2. So L sub 1 is parallel to L sub 2. Line 1 is parallel to line 2. Let's mark that. And then we know that line 3 is also parallel to line 2. So if they are both parallel to the same line, they must have the same slope as that line, which means we can say that line 1 is parallel to line 3. This is also using what's called transitive property. That says if you compare object 1 to object 2 and object 3 to object 2, you could take object 2 out of it and just compare 1 and 3 directly. All right, so that is our third lines theorem. Let's look at a flow proof. A flow proof looks like a flow chart, and it's kind of an interesting little way to do things. Notice the way the arrows are headed. That tells you how to read it. In this case, the statements of the proof go in the boxes. So these are your statements of your proof. The reasons go under the boxes. And contributing information to a conclusion is connected on the sides. Okay, so let's look at this. It says ADB and CDB are right angles. And I don't actually have a drawing to go with this one, unfortunately. So if this is a given, then the reason, meaning they told you, then given would go underneath the reason. ADB and CDB are right triangles. That would be the definition of a right triangle. So they went from right angles to right triangles. So this is kind of the flow of the proof. That's the first one. That's the second one. That would be the reason. So if they are, now this is where the conclusion needs extra information. We want to prove that the triangles are congruent, but knowing they're right triangles is not enough. We have to have something else. So this is where these wings come in. These wings add information to what's been given, and that you connect it directly to what it affects. So we know that they are right triangles. AB and BC are congruent, so two of their sides are congruent. That gets connected, so that comes first. And then BD is congruent to itself. That comes second. So these two reasons get added to the fact that they are right triangles. Now we can say that they are congruent by hypotenuse-leg congruency theorem, which we'll go over later. And then what we want out of this is AD congruent to DC. Corresponding parts of congruent triangles are congruent. So that's how a flowchart proof works. You've got your primary statements down the middle. If you need more than one piece of contributing information, the extra pieces become wings. All right, let's flip the page. All right, this is a two-column proof. Some of this got kind of messed up, so you can put this in L is parallel to M. That's what that should say. Okay, given. Given is information that's true that they tell you at the beginning. Angle 1 is congruent to angle 2. So let's, and that's already marked actually. Here's 1. That's congruent to angle 2. And we want to prove that line L is parallel to line M. You can't use alternate interior angles converse because that is what we're trying to prove. So you can use any other theorems except for that one. All right, here's how your two-column proof goes. You start by stating the givens. 1 and 2 are congruent. Okay. Now, we need to prove this another way. So this one is going to use corresponding angles. So what they want to do is prove that this one and this one are congruent to each other. So 2 and 3 are congruent to each other because vertical angles are congruent. Vertical angles theorem. Vertical angles are congruent. Now we've got, since 1 is congruent to 2 and 2 is congruent to 3, then 1 must be congruent to 3. That's your transitive property of congruence. And since 1 and 3 are corresponding angles, we can say that line L is parallel to M because of the converse of corresponding angles postulate, which says if two lines are cut by a transversal and corresponding angles are congruent, then the lines are parallel. In a proof, if there is a title to a theorem, you do not have to write out the theorem. You can always write out the theorem if you forget the title, but the title is sufficient. Okay, so we are going to start with our given. Okay, so we have angle 1 congruent to angle 2. So the statement goes in the box, the reason goes below. That's a given. Okay. Now, in this one, vertical angles theorem does not attach directly to this, so we're going to have to attach it with an arrow. So adding to that, oops, sorry, I have the wrong arrow. Oops. So we're trying to get to the fact that angle 1 is congruent to angle 3. We want that, but we need another piece of information. We need to know that vertical angles are congruent. So that's going to attach. So angle 2 is congruent to angle 3. And this is vertical angles theorem. So because 1 is congruent to 2 was a given, and 2 is congruent to 3, then we can say 1 is congruent to 3 because of transitive property of congruence. All right, now that we have those two, we can prove that line L is parallel to line M. And the reason would be the converse of corresponding angles postulate. So you really do have to figure out, where do I start? Oh, I'm sorry, I didn't have that in a view. I'll give you a chance to draw that. This is where you start. We want to get to 1 and 3 being congruent, but we needed another piece of information. So remember, needed pieces of information go on the side wings. And then once 1 is congruent to 3, we know that the lines are parallel by the converse of corresponding angles postulate. So that's how you draw yourself a flow proof from a 2-column proof. All right, I hope that was helpful. Have a good afternoon.